is Professor Vassilevski. Yuri, we have checked with all participants, with all speakers, that it's okay with the slides, everything works. So please, you can start the session at your convenience.
I think we shall start right now. I will spend a couple of minutes to introduce Adelia. So, dear colleagues, we start our session. Our plenary speaker is Adelia Sequeira. She is an old friend of mine, and she is full professor of mathematics at Department of Mathematics of Lisbon University. She is coordinator of several activities in this university. In particular, she is a coordinator of the research group at Sequeira Research Institute at the university, which is called Mathematical Modeling in Biomedicine. And actually, she received the first doctoral degree in numerical analysis in 1981 at École Polytechnique, the famous university of France, from France. Then she got a second degree in mathematics in 1985 in the University of Lisbon, and in 2001 she obtained habilitation degree in mathematics, and since 2018 she is a corresponding member of the Lisbon Academy of Science, and in 2019 she was selected as a woman in science by the Portuguese Agency of Science and Technology. As far as I understand, this is an analog of Ministry of Science, right? This agency.
Yeah. Thank you.
And scope from computational fluid dynamics, in particular to viscoelastic and inelastic non-Newtonian fluids, and hemodialysis, of course. And also she is very active in cardiovascular mathematical modeling associated with vascular diseases, in particular aneurysms, cerebral aneurysm progression, and biomechanical and biochemical actions of blood vessels, and of course thrombosis and arteriosclerosis processes. So this wonderful field of interest suggests a very interesting lecture, which is called Progress in the Description of Near-Wall Transport and Hemodynamic Parameters in Cerebral Aneurysm. Please, Adelia.
So thank you very much, Yuri. You said you know everything about my life. Thank you very much. And thank you, Vitaly, and all the organizers for this this invitation. So let me share my slides. I already tried, and it was working. So now. They were working. Is it working? No?
Not yet, not yet.
Not yet. So, now share.
Yes, it works.
It works?
Mm-hmm.
Okay. So thank you again for good afternoon to everybody. Thank you again for these kind words and for the kind invitation to Vitaly and other organizers for being here with you from so far away. And so the topic of my lecture is, in fact, I wrote Progress in the Description of Blood Near Wall Transport in Aneurysms, but this is the last part of my talk. In fact, in general, I will talk about patient-specific computational hemodynamics of cerebral aneurysms, which is one of the topics I'm working on. And there was already a session on cardiovascular diseases, so there is not much to say about this. So everybody knows that it's the leading cause of death in developed countries. And it's very important to study the modeling and simulations of blood flow, behavior, and applied stresses that help to understand diseases and optimize surgeries and medical procedures. So the cardiovascular diseases, there are several cardiovascular diseases. I will be concentrated here in aneurysms. There was also a talk, a plenary talk on fusiform aneurysms. So vascular aneurysms that have this form here, but I will be concentrated on the cerebral aneurysms, which have the form of secular aneurysms and are located in the brain. They are gradual dilation of arterial segments, and the consequences is that the vessel stretches and becomes thinner, and it can rupture, causing the hemorrhagic strokes. Of course, this is the motivation is the mathematical modeling. So mathematical modeling and simulation of the human cardiovascular system is very important to study the development of aneurysms, and the main important issue is to determine the influence of the wall shear stress, which is the tangential component of the traction on the wall. And so the wall shear stress cannot be obtained directly by the medical doctors when they get these medical images. It's a product of the simulations from the velocity and pressure. It's possible to obtain the wall shear stress, which is also an indicator of atherosclerosis. In fact, there is a controversy between low and high wall shear stress. I will talk a bit about this, but for instance, high wall shear stress can, in the case of atherosclerosis, can also indicate the formation of induce the platelet activation, and in particular in the case of atherosclerosis and the rupture of plaque. So what are the difficulties here? In particular, there are difficulties in modeling blood flow, because blood is a very complex fluid, and we can think about blood rheology, modeling blood as a Newtonian or a non-Newtonian fluid, and the interaction of blood with the vessel walls, the complex geometry of the vasculature, and the fact that it is a closed system, and that we do the 3D flow simulations in specific regions of interest, but we cannot do 3D flow simulations in all the cardiovascular system, and the local flow dynamics. But we should couple 3D flow simulations with reduced system, 1D or 0D, and then take into account that the local flow dynamics has an important role in the global system, and vice versa. So I go directly to the aneurysms, to the computational hemodynamics of cerebral aneurysms for patient-specific cases. And in particular, what we want to know is how can computational fluid dynamics can help in the prognosis and therapy of planning. So we know that the cerebral aneurysms, they appear at the circle of Willis, essentially at the bifurcations and curved segments, and they are the most common cause of hemorrhagic strokes. There are typically no symptoms until rupture, but and the mechanisms are not known. In fact, they can grow. There is the formation, the growth, the rupture, and this is still not well understood. And it's important to understand these processes and what can lead to to try to evaluate this progress and how we can treat the aneurysms when they appear. There are some issues that are well known. For instance, the asymmetry of the circle of Willis, the existence of cerebral atherosclerosis, the existence of hypertension, and this non-uniform distribution of aneurysms. So here in these pictures, you can see, for instance, this picture of this lady was given by a medical doctor who, so a neuroradiologist was used to observe people, and looking to the eyes of this person, he realized immediately she had very strong headaches and so on. He realized immediately that there is an asymmetry in her face, that there was something wrong, and then immediately he did some observations, so some computer so OCT, and but in fact they are invasive, and this is not done without being really necessary. Then this is an aneurysm with all the branches, and this is a picture of the simulations, but we will see this later. So when the cerebral aneurysms are detected, they can be treated, or then they can be submitted to a surgery. Treated means that they can be clipped if the neck is not too large. It's the case here. This is the endovascular coiling. And if there is this, they can be filled by this material here, and in this case, it's necessary to introduce a stent. It's called the balloon and stent-assisted coiling. And this stent is put here in order to reestablish the normal circulation. The idea is to dry the blood flow, to dry the circulation in the aneurysms, and to avoid rupture. So sometimes it happens, the problem with the introduction of the stent, it's necessary to take some anticoagulants and so on, because the formation of clots can appear, and so, but they are very used to this, and so this is some procedure which is very well known and used by the neuroradiologists. The neurosurgeons, they just do the surgery, and that's all. So this is just a picture that I like to show, because you can see here all these branches and how the complex is the cerebral vasculature. And when it appears one aneurysm, there is more than one, and so we must be careful with this, because sometimes people they have a surgery from one aneurysm that ruptures, and suddenly the medical doctors discover another one which is about to rupture, and they because usually there is more than one dilation. So this, in fact, cerebral aneurysm is a multifactorial problem. In this cartoon here, this pipeline, you can see here the aneurysm, the initiation, growth, stabilization, and rupture. And the several contributions to this are of the clinical. There are clinical aspects, of course, genetics, gender, age, smoking, history of hypertension. So also the peri-aneurysmal environment, the sharp contacts, smooth contacts, and so on. You can see here in this frame here. And mainly also, we are mainly concerned with hemodynamics, but also with biomechanics, the wall stress and growth that leads to growth and remodeling. And hemodynamics, as I said, there is this controversy between low and high wall shear stress. Why? Because low wall shear stress induces endothelial dysfunction, then remodeling and intimal thickening, and high wall shear stress, excess of nitric oxide apoptosis, degenerative remodeling, and wall weakness. So both wall weakness or intimal thickening can induce rupture. And so sometimes in this framework of aneurysms, in some papers we can realize that some authors say that this is a region of high wall shear stress, so it's prone for rupture. This is a region of low wall shear stress, it's prone for rupture, but it depends. So high wall shear stress, for instance, in bifurcations, of course, there is the formation of aneurysms, and of course there the wall becomes weaker, and of course it's possible the rupture is possible. But this is to tell you that looking only to the wall shear stress, and the values, the magnitude is not enough. So it's necessary to do more. And so this is the pipeline. So so the image acquisition, first we start from real patients, image acquisition from the circle of Willis of the aneurysms, then image processing, and by all the techniques of image processing, so image segmentation, surface extraction, smoothing, and then meshing, we obtain the geometries and we use the appropriate numerical simulations using the models. The numerical models of hemodynamics can be the Navier-Stokes equations on there, or then a model like non-Newtonian, generalized Newtonian. We realized that the difference is not very big. So the difference between Newtonian and generalized Newtonian is not something that deserves too much attention, in fact, at this level. So some generalized Newtonian model can be used here, and we see some differences, but using Navier-Stokes equation is enough for obtaining some relevant results. Okay, so from the geometry reconstruction, then we look to the usual measures, which are tangential to the wall. And as I said, it's the wall shear stress. So, so the tangential component of the traction on the wall, or the viscous force acting, working parallel to the vessel wall. And then some indicators that derive from the wall shear stress that I will define a bit later, the OSI number and the relative residence time, and others that I will talk about later that are less explored measures that are normal to the wall as the mass transport process, so the near wall measures mass transport process to and from the wall and the wall shear stress critical points. And then so the biomarkers that it's a correlation between the correlation between hemodynamics and biochemical factors. So this is the biomarkers on the wall that it's important to also to care about this. Okay, so now this is so you can see the rotation CTA and some projections. The maximum intensity projection, so we take some projection and then we choose our extract the aneurysm, the region that we want to study, and then we can select the aneurysm with branches or without branches. Of course, the results are different if we select just this region or if we extend the vessel, or if we consider also the other branches that surround the aneurysm and the parent vessel. If we take into account the other vessels, we can and we don't want to do the 3D or 1D 3D simulations, let's say, or even 1D simulations, we can account for these branches by considering appropriate boundary conditions without considering the explicit coupling between 3D and 1D models. So this can be done, and so here you can see the coupling between 3D with 1D by considering continuity of the flux and the stress from the 3D to 1D. So from the outflow conditions, there are 4 different outflow conditions that are analyzed for the side branches. You can consider no slip, it's just neglect the side branches, or traction free, no tangential stress component, or coupling with the 1D equivalent to a 3D side branches, or coupling with the 0D resistance model, which is based on the 1D model. So there are different possibilities of coupling. So I don't go into details here. So for the numerical simulations, we use, of course, so open access codes that exist online. So for the automatic and manual segmentations, ITK SNAP, surface smoothing suitable for simulations, mesh slab, the creations of extensions. This is important because in order, it's necessary to use some artificial extrusions and to extend the vessel. Usually it is 20 times the compared to the inlet diameter in order to have a fully developed flow. And so to this geometry manipulation, it's possible to use this mesh mixer. and the Gmesh for meshing. So all of this is available online. So for the numerical simulations, it's possible to use different schemes. As I said, we were using the Navier-Stokes equations. I don't specify here so I will do it later, the boundary conditions, but it's here, okay, the inlet boundary conditions. But so for these Navier-Stokes equations, which are the equations for the blood here, we use finite elements, Phoenix software, but we can also use finite volumes, open foam, H2, H1, finite elements in order to obtain an accuracy of order 2. Of course, we need some stabilization procedures. If we use H1, but with H2, H1, it's fine. And for time discretization, we use the incremental pressure correction scheme. So we solve for an intermediate velocity, then we solve for the pressure, and then we update the velocity according to this expression. So now I need here something to help me, because so we analyzed in fact 6 different patients. All of them are females. The ages are marked here, different ages, and they of course, you know, the problem here in order to get results, relevant results, is the number of cases that are analyzed. This is a deficiency of these studies, is that we don't have enough data to derive appropriate conditions, appropriate solutions, appropriate conclusions, I mean. It's necessary to do many studies, and the conclusions are always not, they are patient specific, and we cannot extrapolate to all patients because we don't analyze too many. These neurosurgeons, they gave us lots of cases, but they were not treatable from the point of view of the geometries. The geometries, the images were not good in several cases. Many cases, they gave more than 100, and then we could only select 6 that were available for the geometries to do appropriate treatment of the geometries. And so these are the ones we selected. So the ones here are, so the first one, the first case is a female. She has a unique aneurysm located on the left-hand side of the posterior inferior cerebral artery called PIC region, which is a region prone to rupture. And this aneurysm has been ruptured when and then submitted to surgery. Then the case 2, it's a female with several aneurysms. She has multiple aneurysms. This was incidentally detected, no rupture. It was submitted to surgery. The one that was submitted to surgery was not, in fact, prone to rupture. But you know, the neurosurgeon, when they see an aneurysm, they cut it. And this lady had more than one, and it decided to cut this one. And it was important for us because we had material then for the other studies. And so this is the case 2, and the case 3. This is a more singular case because it's a complex aneurysm with atherosclerosis and a very unhealthy aspect. You will see the aspect of this aneurysm. It was ruptured during a surgery located at the anterior cerebral artery, AC. The case 4 is a unique aneurysm located at the MCA, middle cerebral artery, potentially dangerous to rupture, so they decided to cut it. The case 5 is a unique aneurysm located on the left MCA, so the middle cerebral artery, incidentally found, and the surgery was performed with rupture. And the case C was already ruptured aneurysm and located at the anterior cerebral artery. So these all cases are, each case is different. They have a different neck area. Only this one could be submitted to treatment. The other one, or even this one, perhaps the other ones are, or no, this one here. The other ones are very large, could not be submitted to treatment.
Dear Adele, excuse me, could you hide the message at the bottom of your screen? Just
how can I
press just hide? You see hide on the right of the message.
Hide.
Yes.
And now.
Yes. Now it is.
It's okay.
Yes, perfect.
Okay. No, it was also important for me because I didn't see the bottom of my screen, and so now I see it. Yeah, I didn't know how to do it. Okay, thank you, Yuri. Thank you.
Great.
Okay, great. I thought that only me could not see this message. Okay, thank you. So the here you can see that for the numerical simulation, of course, we did a convergence study, and since the inlets are different, we had to rescale to correspond to a Reynolds number, the same for all of them, 450 Reynolds number, since there were different inlet areas associated to different patients. We consider wall rigid. We could also consider a moving wall, and interact with a model for the wall, but in this case it was a rigid wall. Traction-free boundary condition, and this is what we did. Okay, so now some hemodynamic parameters. So we have velocity and, of course, wall shear stress. So this is for the first aneurysm that I talked about. Here we have the streamlines. So the streamlines, so the velocity profiles different three slices, and the vorticity at peak of diastole, mid diastole, and level of diastole. And we computed 3 cardiac cycles using 800 time steps per cycle. And we took the images at the end of the 3rd cycle. Now, for the wall shear stress, here you can see the same for the wall shear stress, but for the 6 aneurysms. So this is the aspect of the 6 aneurysms. This is the bad one of this lady, 95 years old, who had atherosclerosis, atherosclerotic, very unhealthy aneurysm that had a rupture, and it's this one which is different from the others. So all of them are different. This is the problem in these studies. So also for peak of diastole, mid diastole, and end of diastole. So this is some movie that goes slowly, but I don't know how much time I have, but yeah, I still have not much. Okay, I need to go fast. So this is the velocity vector field. This is velocity profile. Oh, okay, now we can see better the hemodynamic parameters, wall shear stress. This moves faster. This is for another aneurysm. This is also for the wall shear stress. And then this is wall shear stress. So this takes always some time. So I hope you can see the movies. I inserted them here. Okay. Now, since only the wall shear stress is not enough to give us some information, so we take also, so T is the cardiac cycle duration, and we take the time average wall shear stress and the relative residence time, which is the inverse. And the relative residence time is important because it gives an indication of the near wall stagnation. And the OSI number is also important, given by this expression. It varies between 0 and 1/2. And 0 indicates no oscillatory wall shear stress throughout the pulsatile cycle, and 1/2 indicates oscillatory wall shear stress. And so between that, between 0 and 1/2, we have these values. So I wall shear stress gradients, I OSI number, I RRT have been reported to increase the risk of rupture. So not only looking at the wall shear stress, but wall shear stress gradients and I OSI number and the IRRT indicates this. Okay, now the near wall region. The near wall region, this is the definition. So is the lumen endothelial interface where the blood flow interacts with the endothelial cell layer. It's important to understand the physiological functions of the vascular system and how the mechanical forces act in the transduction in this region. So it's not straightforward to study this due to the no slip boundary condition. So, however, from the near wall convective transport can be derived by Taylor expansion of a fluid element trajectory in a moving reference frame in the limit of the wall. And in addition to the tangential transport, we have the normal transport. So we are near the wall, and we obtain this wall shear stress divergence. When it is negative, it indicates that the flow goes towards the wall, and when it is positive, the flow goes away from the wall. So this is an indicator that is important for the to give an information. So it derives from the wall shear stress, but it's another indicator that helps to obtain some information about the progression of the aneurysms. So a part of this function is the mass transport process. If the flow goes away or towards the wall, it's the mass transport process from the blood to or from the vessel wall. So the critical points are the wall shear stress are the points where the wall shear stress are equal to 0, and they can be of different type. We can obtain critical points of different type. Here you can see some pictures. This has been obtained for the different also for the different aneurysms and the surface shear lines and streamlines. And they can, so the near wall region and critical point analysis can provide important insight into a better understanding of the cerebral aneurysm occurrence and progression. So there are unstable nodes, stable nodes, and saddle points, stable spiral, unstable center, and so these critical points. So we have a paper on this that I will show you. So just I have some figures here for the pressure, the wall shear stress divergence, and wall shear stress that in the shear lines for one of the patients, and this is for patient 2. We took this here. In this case, we only studied 3 of these 6 patients. We only studied 3 patients for this case. Okay, so this is for the peak of systole, mid diastole, and end of diastole for patient 1 and patient 2. I only show the results here for these two patients. And this is the combination of the wall shear stress divergence and surface shear lines with the critical points. You can see these critical points here where the wall shear stress is equal to 0. Okay, so the conclusion.
Adelia, you have 2 or 3 minutes only.
Oh. Okay, so just if you want to know more about this, we have a paper here. The near wall in cerebral aneurysms, and so the strongest persistent stable spiral points based on the wall shear stress divergence magnitude. Can find it here. So this is something about the biomarkers on the wall that recently we have obtained some results for this. This is a work still in progress. This was given, so it was made by some experimentalists in collaboration with the medical doctors. So after the surgery, they removed a part of the aneurysm sac, and the aneurysm sac was removed, and the part was marked for study, histological study. And then there was the idea was a combination of an experimental procedure with the computational fluid dynamics. So here you can see the wall shear stress distribution and location of black circles here of the tissue samples for the high wall shear stress, medium, and low. So I don't have much time to talk about this, but I will tell you just that we have used gap junction proteins connexin 37, connexin 43, and the molecular chaperone regulator 3 to detect to study as biomarkers. We realized that this BHE3 is not very relevant compared to the hemodynamic to hemodynamics, and the connexin 43 is important for high values of wall shear stress, and the connexin 37 is important in the case of the unruptured aneurysm, which is the P3, because we studied 3 cases here. The unruptured is the P3, and the P1 and P2 are not ruptured. So I have no time for this, just to show you these images that were obtained by the biomarkers on the wall. But this is a work still in progress, because we only studied these 3 cases, and then we compared also with the relative residence time and time average wall shear stress, and the large variations of the wall shear stress divergence, and the zones where the high wall shear stress divergence changes more compared to the others where there are not so big changes. So, and the connexin 43 is the more relevant in the as biomarkers. So, my collaborators, I want to thank all these sponsors that have been involved in this work, and my colleagues, Jorge Tiago, Yolanda, the student who did this work, Alberto Gambaruto, and Ricardo Pereira, the neurosurgeon who did these important surgeries. Okay, thank you very much. Sorry.
Thank you very much, dear Adelia. Very nice talk. Questions? Yes, please. Please, Vitaly. Let me to read it. Or maybe you just talk.
No, I can ask like that.
Yeah, sure.
Thank you, Adelia, for this very interesting presentation. Since we don't have much time, I will ask a short question. We listened yesterday a talk about aneurysm modeling, and the author suggested that the maximum of wall shear stress corresponds to the rupture place. So they suggest that the rupture of aneurysm occurs at the place where wall shear stress is maximal. Do you have the same observation? Can you confirm or maybe not this result of this observation?
Yeah. So, so as I said, so there is a controversy because so the wall shear, the maximum wall shear stress is related to so induces the wall weakness, but the low wall shear stress induces also endothelial dysfunction and remodeling. And so both of them can induce rupture. But of course, in the case of aneurysms, since high wall shear stress appears in certain regions, for instance, in the case of in the bifurcations where the aneurysms appear. So in some regions where the high wall shear stress appears, it can happen the rupture. But there are other regions with low wall shear stress, and if you look to I have shown the wall shear stress in the balloon, and it's blue. Most of it is blue, and the rupture it's not in the neck, in the region of where the wall shear stress is higher. Sometimes the balloon ruptures, the aneurysm ruptures not in the neck but in another region, because there is jets which are with very high under high pressure, and so these jets have a big influence, and there are critical points there where the wall shear stress is equal to 0, and so there is the other influences, and as I said, so the high wall shear stress gradients are more important than to look only to wall shear stress. It's the gradients, it's the OSI number, it's the RRT, IRRT. So that's why we are looking also to the near wall behavior.
Okay, thank you. I understand. Okay, and Alexei Tokarev wanted to ask you, right?
Yes, thank you. Dear Adelia, I'd like to know more about this measure flux to the wall, which you used. Well, could you please explain? Do you integrate some volume flow in the thin area above the wall, or how do you obtain this measure? because when you solve flux to the wall, the normal flux to the wall.
Wall shear stress divergence.
The wall shear stress divergence is it's the wall shear stress divergence is the normal component. So when we consider the Taylor expansion, so in a moving reference, in the limit of the wall, there is the tangential transport and the normal transport. So the normal one is so it comes from a Taylor expansion, and the normal one, the normal component, is this normal component is this divergence.
Yes, but the boundary conditions are zero normal flux. Yes.
Sorry.
But the boundary conditions for equations are zero normal flux. So I don't understand why the limit is non-zero.
Zero normal fluxes.
Boundary conditions for transport equations are zero normal flux, as I understand. So I don't understand why arterial expansions gives you non-zero normal flux. That's the question.
No, but so near the wall, near the wall, so you don't have zero.
Ну я хорошо, тогда подключайтесь, я продолжу.
You don't have zero normal flux there. So you have you are going to study the critical points there. It's before. No, I didn't understand well.
No, excuse me. Yes, I'm sorry to interrupt your discussion, but we are late for our next talk, and moreover, we have some connection problem, and our chairman Yuri Vassilevski is now out of connection. So yes. I will. You are back. So please,
I'm back. Yes.
Yeah, please continue with the next talk, please.
Yes. So Adele, thank you very much. We have to be in rush, and let us thank you very much.
Okay.
And we proceed to the next speaker. The next speaker is Sergei Simakov from Moscow Institute of Physics and Technology and from Sechenov University. His talk is computational evaluation of the effectiveness of coronary revascularization. Please, Sergei.
Okay, thank you. So let's start with this talk. First, I would like to remember what we have done, and some other group. There is a hot and important question whether to place a stent to the coronary artery or not, because the stent placement involves some surgical treatment, some specific complications, and so on. So it is important to understand so-called hydrodynamical importance of the atherosclerotic plaque. The decision on the necessity of stent placement is made based on this hemodynamical importance. There are several approaches, and one of the so-called best approaches, maybe some widely used approach, is the fractional flow reserve computation, which is measured during vasodilated administration, and which produces the maximum possible hyperemia of the vessel, and the intravascular device measures the pressure before and after the stenosis, and the fractional flow reserve is the ratio of these two pressures. So if this ratio below some threshold, say 0.75 or 0.8, something like this, then surgical treatment is needed, and otherwise the patient considered as relatively healthy and no stent placement is required. So this approach have some drawbacks, and we already know how to resolve them. So this measurements of the FFI includes intravascular measurements, which is somewhat similar to the surgical procedure, and introduces expensive and single-use device. And these two drawbacks are somewhat technical, but the third is a principal limitation, which is as a complication of the analysis in the presence of several stenosis. So we already developed a computational tool for assessment of FFI on the basis of individual non-invasively collected data from MRI, CT scans, angiography, arterial pressure, some heart rate, and other parameters from the patient, which can be collected non-invasively. And the result is quite good. So, and our and other groups, several other groups in the world, achieve some good results in this in this task. But there are a lot of other problems which still not be resolved. So one of them is sorry, two of them are the ineffective revascularization. So what if we measure the same parameter FFR after stent placement? Probably we will see the good FFR or bad FFR. But due to the impairment of myocardial circulation, the good FFR value may lead to false negative results. So we can see that this is a good situation, but actually the perfusion of the myocardium may still be low. And the second problem is that the computational evaluation of FFI in patients with impaired myocardial microcirculation is not so obvious, and it was not performed. So actually, the downstream outflow conditions in previous models didn't include some properties of microcirculation region. So and let's remember what is the heart and the heart circulation. So we have two chambers, and actually a very important chamber is the left ventricle, and all chambers are composed by myocardium tissue, myocardium muscle, and the ventricles eject blood to the arteries, pulmonary, and aorta. And some small portion of blood returns to the myocardium by the left and right coronary arteries and their branches. So we have the blood, so the left ventricle pushes the blood, and some blood returns to the heart and supplied with the nutrients. So it's somehow different processes, but we have to combine them in our model. So the perfusion assessment may be performed by different methods, but one of them is the CT perfusion method, and we consider the left chamber as the most important chamber of the heart, and it segmented by a standard 16 segments, which are presented on the slide. So here we have just a scheme, just from the view from the apex, from the down. Just to so this is not this figure C is somewhat not the real structure, but just a representation of this standard segments. So the CTP process includes the some perfusion parameters assessment by iodinized contrast agent administration to an arterial blood, which then flows through the microcirculation, through the subendocardial and the epicardial part, and it attenuates. And this is performed and observed in two conditions, in the stress and rest conditions. So rest conditions are normal conditions for the patient, and the stress conditions assume some physical other stress, but actually it is activated by, again, vasodilated administration, which is similar to the FFR measurements. After that, we have such a scheme, such a picture, and we see here some values of some coefficient in every segment. So this coefficient is called transmural perfusion ratio, TPR, which is the ratio of subendocardial mean attenuation density to subepicardial mean attenuation density. So this parameter is somewhat not physiological, but its value correlates with the perfusion ratio, and it's somehow interpreted by the doctors and allows them to make some decisions. So if TPR between 1 and 1.4, it's considered as a normal case. If TPR below 1 and more than 0.95, then we have a moderate impairment, and severe perfusion pathology observed for TPRs below 0.995 and 0.6 is rarely observed and below value. So it's just some theoretical value. The main observation, which is important for doctors and for construction of our model, is that the lower TPR corresponds to the increased microcirculatory damage and higher terminal resistance. So we include these values, and here in this work we consider just one patient and one case, and here we see some moderate, the region with moderate impairment of myocardial perfusion and relatively normal under stress conditions, and relatively normal perfusion in other parts in every condition, but this for this one patient. So that was the first part. It's perfusion characteristics of the myocardium. The second, we use the CT data to reconstruct the structure of the coronary arteries, the algorithm implemented by our colleagues, and it allows to construct the 1D graph, 1D scheme, based on the CT scans of coronary arteries. So schematically, we have somewhat like following: so the right coronary artery and left coronary artery, and we see we can observe that a lot of vessels are hidden due to the low resolution or due to the low contrast or something like this. But we want to construct the model which supply every segment by one single vessel. So we assume that some vessels are hidden due to the low resolution, for example, and we add them manually. They are presented by dashed lines. So these vessels were added to the model based on some our expert decision or some heuristics. But the parameters of this vessel are similar to the smallest vessel which we actually observe. Of course, there are a lot of smaller vessels, but they're hidden from the measurements. And then we assign every terminal vessel to one segment of the microcirculation, and then we can state some specific boundary condition in every segment based on the actually observed in patient TPR values. So these are parameters, and we see the TPR values for those vessels which connected to the perfusion regions. And here, this is some intermediate vessels, so they don't have the TPR values. We have 16 terminals and 16 TPR values. And then we simulate the blood flow in the 1D network by this hyperbolic nonlinear set of equations, which are derived from Navier-Stokes equations and represent the mass and momentum conservation. And they are extended by this wall state equation, which was somewhat analytical function based on the actual observation on elasticity of the vessels. But one important note states that actually these equations are not hyperbolic if we derive them honestly from the Navier-Stokes equation, but under some conditions, so they should look like this. But of course, it would be better to have a hyperbolic set, so we can use some specific numerical methods and can compute them quite effectively. So if we consider the second equation, and if we substitute the flow Q by the cross section to the velocity product, and if we reverse the wall state function, so we to take the cross section as a function of pressure, and substitute to this second equation here, to the momentum conservation equation, then we observe the following formula, which have a small parameter epsilon, which is looks like this for the specific wall state equation. Actually, every wall state equation for the vessels is a S-like monotone function, so it's should be reversed in a similar way. For our specific case, the epsilon looks like this, and it's really a very small parameter in a wide range of physiological parameters typical for the arteries. Actually, this is not the case for some veins, but for arteries it works well, and we take the hyperbolic set as a correct relevant model for the blood flow, as a one-dimensional model of the blood in the coronary arteries. So this is the model for the flow in one artery, but it should be extended to the network by boundary conditions. In every vessel junction, we consider the mass conservation in this form, and the total pressure continuity in this form, and it also extended by conditions for coming from along the outgoing characteristics of the hyperbolic set, but it's not considered here. So it's the same for every terminal point. And what is important is the left ventricle outflow condition, which states like this, where Q is some time-defined function, which depends on the stroke volume, which can be computed for every specific patient. And it also depends on the duration of systole. So the systole also can be evaluated for some specific patients. So this function is set specifically for every patient, where the stroke volume actually can be computed like this. So if we have, for example, various heart rate, various abnormalities with the heart rhythm, we can this function will change. And this parameter, the duration of the CISL, relates to the total duration of the heart cycle T by this model of actual potential duration at 80% for polarization. So we derive this relation, and actually we every parameter depends on the heart rate or on the duration of one cardiac cycle. And there's an experimental dependency coming from some clinical works, is the dependency of the stroke volume from the heart rate, or again, the heart rate is inversely connected with this duration of the heart cycle. So in this formula, everything as stroke volume and duration of the CISL depends on the duration of the heart cycle, which can be easily measured for every patient. And outflow boundary conditions for coronary arteries specifically also depends on the duration of the CISL, because during CISL the myocardium contracts, and actually it stops the blood flow in the terminal coronary arteries. So we impose these outflow conditions. We can suppose that every artery is connected to some venous reservoir of some constant pressure, 8 millimeters. And it also multiplied by, so the most important part here, the most specific part for the coronary circulation is resistance, hydraulic resistance R, which is some time-defined hydraulic resistance depending on the duration of the CISL, and with some coefficient which is proportional to the myocardium impairment coming from the CTP data of microcirculation. And also we here have to define the hyperemic hydraulic resistance for the stress state conditions, which is 0.3 times the normal diastolic value of the hydraulic resistance. So here we consider the R small, here the actual resistance, and the alpha coefficient, which depends on the CTP data, is defined as follows. So we set it to 1 if we have some normal state, and we have some exponential decrease of this coefficient with the increase of this coefficient with the decrease of TPR. So TPR, so we set this coefficient ABC as 1 for some normal healthy value of TPR, and some very big value for some very small and even unrealistic TPR, which completely stops the flow even during TSL in the terminal vessel. So taking this update of our previous model of the coronary circulation, we performed several numerical measurements, some simulations, and the actual patient has 3 stenosis in the one branch of left coronary artery, and we consider the stenosis 9, which was the most 85% decrease of the lumen, and the measured FFI by this transducer invasively is 0.43. So we simulate this FFI either by regardless CTP, so taking our previous procedure. So at every point and every vessel we set some healthy value of CTP, so alpha was 1, and we see that relative error is almost 10%. And when we set CTP, so TPR, sorry, TPR and alpha for every terminal depending on the CTP measurements. We get this value 0.41, so the relative error is less than 5%, so it's two times better. But just for one, unfortunately, at the moment, just for one single patient. So we waiting for more patients, for more the data to check our model. So and just one set of another set of simulations, and it will consider the three parameters. One of them already discussed, FFR, fractional flow reserve, and there are also other two parameters which also characterize the blood flow near the stenosis, through the stenosis. It's a coronary flow reserve, which is the ratio of coronary blood flow during drug-enabled maximum hyperemia. So it's again the stress conditions for the CTP measurements. And to the CT at rest. So we need again both stress and rest conditions. For FFR, we just need stress conditions. And the third parameter, which doesn't require administration of the vasodilators, which is very good. It's an instantaneous wave free ratio IFR, which is the ratio of distal coronary pressure to the pressure in the aorta over some specific wave-free diastolic period, which is manually computed from the analysis of diastolic curve part of the pressure. So it again doesn't require administration of some vasodilators, so it's very good, but it's somewhat maybe difficult to measure. And the most difficult parameter is coronary flow reserve, because it is the direct measurements of the flow is very difficult due to technical reasons. So anyway, we can compute all three parameters by our model virtually, and we compute them for the two cases. For the cases, we remove stenosis from the model, and we consider this 85% stenosis in the vessel 9. And we compute FFR, CFR, and IFR for various values of TPR. So 1.4 relates to some healthy microcirculation, but presence of the stenosis. Yes, and then we decrease this TPR and see what happens. So we can observe that if we have no stenosis, then in every case, every parameters are almost not changed. So it's almost the same. And the model is sensitive to this. So it's the problem only microcirculation, but it can be measured by this, of course, this parameter. So, okay, this is normal situation. But if we have a stenosis, then we may have some misinterpretation. So we can see the higher values of every parameter, FFR, CFR, and IFR, for some in some microcirculation impairment case, say 0.6, for example. Yes, so we can observe the better situation, but actually it is not so good. So if we don't consider, so we can see that everything is bad, but actually it may be better for the hemodynamic importance of this stenosis region. Okay, so this is the end of my talk. So some conclusions of our work are that acceptable values of FFR after treatment may be observed after even an effective revascularization, which leads to a false negative results. So impairment of microvascular perfusion plays a significant role, of course, for evaluation of hemodynamic indices. Some drawbacks of this work, the disadvantages are that, of course, we need more clinical cases to state something more statistically proven. And some other methods may give better accuracy, but again, we used the CTP data, which are not very, maybe very good, but they are available in everyday practice. So if we manage to develop this statistically proven model based on CTP data, not on PET-to-SPECT, then it is good for some everyday practice in many clinics of the Russia and of the world. So I acknowledge the help of my colleagues, and some work was supported by these grants. So that's all. Thank you.
Thank you very much, Sergey. Questions? If people are thinking, I have a question. Alexey Belyaev, please. Alexey.
Yes, Sergey, thank you very much for a very interesting talk. I wonder what are the criteria or numerical conditions under which you could recommend the medical specialist to give a recommendation for operation or a stent implantment in patients?
Actually, it should be discussed later. So if we consider the microcirculation impairment, yes, we just okay. So actually, we already answered to this question by our previous model. So if FFI below 0.8, 0.7, then as a stenting is recommended by our model. But if we include some data regarding the state of microcirculation, then we can increase accuracy of these predictions. So, so this is just some update of this model, and it makes it more correct.
Okay, thank you very much.
Okay, since we are running out of time, so thank you very much, Sergey, for your very interesting talk. And we proceed to the next speaker, which is Alexey Belyaev. Please, Alexey.
Yeah, good afternoon, dear colleagues. I would like to share my screen. Now, I hope you can see the presentation. Today, I would like to talk about molecular things that happen during primary hemostasis in arteries and microvasculature. Basically, I would concentrate on mechanobiology and mechanical effects which happen in the molecule of one Willebrand factor protein. And we'll devote your attention to multiscale computer simulations. The thrombosis is a side effect of the hemostatic response. Sometimes when the wall of a vessel gets injured, the aggregation of platelets can happen on the wall, and this platelet aggregate may be surprisingly stable to withstand the flow and the drag force from the streaming blood. And also this phenomenon is accompanied by the coagulation of blood plasma, but usually when the flow conditions are very strong, the platelet aggregation happens as a first stage of thrombus development in a vessel. And that's why it is important to know how this initial aggregation of platelets happens and what is the mechanics involved in this process. The blood platelets are known to interact through a series of specific pairwise protein-protein interaction due to specific receptor proteins on their membranes, and also some proteins that are dissolved in the blood plasma. But mainly, the initial stage relies on the interaction of this GP1B59 receptor of blood platelets with the plasma-borne soluble 1 Willebrand factor multimeric protein. In this picture, we can see a microphotograph of aggregated and highly activated platelets. And in this one, particular from the review of Timothy Springer, we can see the electronic microphotograph of von Willebrand factor as it is on some substrate. We can see that actually this is a very long protein. It can be longer than several hundreds of nanometers. In fact, it can be as long as several tens of micrometers. It consists of subunits, known dimers. It is a linear polymer, but each dimer has its own substructure, and they are connected through each other rigidly. The main goals and the main tasks of this work that I'm going to report today is to build a multiscale computational framework, three-dimensional framework for prediction of thrombogenesis in microvasculature based on the mechanics of the system, based on the mechanical effects in the proteins, in the blood cells, red blood cells, and platelets, and so on. Therefore, there are specific tasks to be solved, and I will speak about the construction of the model for von Willebrand factor protein in its multimeric form, its behavior in the flow of viscous fluid. Also, a bit will I speak about model for platelet aggregation through this von Willebrand factor mediated interaction, and also about the introduction of red blood cells to reproduce the erythrolytic mechanics and hemodynamics of the whole blood, together with platelets and von Willebrand factor. Well, if it turns to modeling, we also have to find some compromise between the details of our model and the length and time scale that we would like to simulate. Basically, it is known that molecular dynamics simulation provide a lot of detail, but it's not capable of simulating the system getting the trajectories longer than several hundreds of nanoseconds. Of course, the thrombosis process takes from several seconds up to several minutes and sometimes hours. And these models are only capable of reproducing the mechanics or the effects of aggregation of individual proteins, maybe on very limited time scale. In the contrast, one may consider continuum modeling, although there are some limitations of this approach as well and some uncertainties in this approach. But it allows us to simulate several seconds, tens of seconds, hundreds, and even minutes. But I will speak a bit in detail about such approach next week on the workshop organized by Yuri Vassilevski. That's a bit of an announcement. And today I would like to focus on something in between, on mesoscale models, which on one hand allow us to simulate considerably long time scales and length scales of several tens of micrometers and several tens of seconds. But on the other hand, they allow to a known extent simulate the mechanics of von Willebrand factor protein involved in the platelet adhesion, and which is also known to be responsible known to be responsible for primary hemostasis and is susceptible to blood flow. So there are different approaches that we use. I will speak about mainly this piece of work, and also will speak in the end about this more detailed model of von Willebrand factor that resolves individual domains. So general lattice-Boltzmann particle dynamics model is a hybrid model. We consider particle dynamics for the movement and mechanics of individual species that are present in the model, mainly red blood cells, platelets, and von Willebrand factor multimers. However, for the fluid dynamics itself, we keep the continuum description by implementing the lattice-Boltzmann method, which is based on the solution of this kinetic Boltzmann equation, but in a discretized phase space, which consists of three spatial dimensions and three velocity dimensions. This discretization scheme used in our work is D3Q19, which means that we solve the equation in three spatial dimensions and use 19 vectors to discretize the velocities. This is the set of equation, and the details are presented in a number of publications and books. It's quite classic approach, so I only give a link to the book. The particle dynamics is also very well known approach, but the thing is which coupling procedure we are using to link the movement of cells and species in our model with movement of fluid. In this particular work, we use viscous force or Stokes-like coupling, described also in a number of publications, basically in Dudnik and Ladd work presented here. The idea is that we use classical molecular dynamics modeling based on solution of Newton's equation. On the right-hand side, we have the sum of the forces present in our model. For description of cells, we use the specific phenomenological description of elastic forces to maintain the rigidity of membranes and surfaces of the cells. Also, we have the interaction forces that actually allow for the adhesion between platelets and von Willebrand factor, and the viscous force, which allows for coupling between the fluid and the cells. Elastic forces are represented by stretching force, which is taken in the form of Neo-Hookean law. Bending force, which depends on the angle between two faces. Area conservation and volume conservation forces, and this model is actually also taken from prior works. For the interaction forces between different species, between different types of particles, we use Fene potential first for the for making the polymer actually solid and resistible to any forces. Also, we use special Lennard-Jones like interaction for adhesion, for attraction between von Willebrand factor monomers, and also we use the Morse potential for modeling the adhesion between von Willebrand factor and platelet. On the surface of platelets, we place several number of receptors which imitate this GP1B receptor in real life. And von Willebrand factor is presented, each dimer in this model is presented as a sphere, as a bead on a spring. And we actually measure these amplitudes and the parameters of this interaction using steered molecular dynamics, using GROMACS, and we apply umbrella sampling procedure for measuring the parameters of this potential. For the viscous coupling, as I have said, we use this Stokes-like force acting on each particle on the membrane of each cell or red blood cell or platelet. We validate this approach using known analytical solution, Goldman-Cox-Brenner's theory mainly. We see that in particular cases, this validation is successful. For the protein dynamics, we also use the same method in general, but we prescribe each friction coefficient for each type of species, type of particles present in the system. And the interaction between each bead in von Willebrand factor is also specifically tuned up. We considered the mechanics of this protein in a plane shear flow, changed the shear rate, and compared to known experimental and simulation work by Schneider et al. And we considered that we see that this such description is quite sufficient to demonstrate conformational changes which are triggered by the increase of the shear in the simulation in the model. For red blood cell validation, we also used a lot of procedures, mainly putting the red blood cell into shear flow and measuring its sizes, stretching, and also we measured the tank threading frequency And the threshold for this tank trading motion, it fits experimental data quite well for a particular set of parameters. We also compared this to optical tweezer experiments by stretching each individual red blood cell without the shear, and the results are indeed quite satisfactory, but I don't show them for saving time in this presentation. Maybe we'll show it later. The results. Now let's come to the results. The first interesting notion that was derived from such a modeling was that the length of von Willebrand factor multimers grafted to a surface in a shear flow is indeed important for allowing platelets or particles adhering to these von Willebrand factor multimers for allowing them to withstand high shear rate. We take the shear rate of around 1,000 up to several thousands of inverse seconds, typical values for microvasculature and some arteries. And we see that there is no threshold for the length of von Willebrand factor, which allows it for successful mediating the adhesion of platelets to such surface. And there is analytical formula which could be derived for the critical shear rate. For each value of shear rate above this critical value, the adhesion is not happening in the model. However, if the shear rate in the model is below this critical value, we observe that the adhesion is more or less stable and platelet can stick to this von Willebrand factor grafted solidly to a surface. So we know that the size, the length, the control length, the number of multimers in von Willebrand factor is really important, and it should be quite long to allow for platelet adhesion. And the principle is basically a mechanical thing. It's similar to mooring a boat in the marine, for example. Like we have the tension force directed along the stretched part of von Willebrand factor, and we have the drag force from the flow, and we want this component, the tangential component of this tension force, to be as big as possible. And it's obvious that only for a long mooring here it is possible. However, if the von Willebrand factor is quite short, the maximal stretching force is not attainable, and the drag force just washes the platelet away. We also observed that shape of the platelet is quite important, and the oblate shape of the platelet allows it to withstand a greater shear rate and greater drag force. And because the orientation of platelet when it's adherent to surface is so that the less drag is experienced by the platelet, and also that the greater effective surface is available for binding with von Willebrand factor multimer. In this particular video, I hope you can see that platelets and spheres bind differently. Then we move to the simulation of whole blood in microvessel, including grafted von Willebrand factor multimers. This reproduces the situation when there is an inflammation of the vessel wall, and the inflamed endothelium can expose von Willebrand factor. And we wondered how the platelets would interact with von Willebrand factor if there are red blood cells present in the system, and they could mechanically interact with platelets. One thing that we noticed that platelets are indeed pushed towards the vessel walls, which is quite known from experiments. The other thing we noted that in the narrow vessel, actually this is more typical, this size is typical for capillaries. The red blood cells push and slide platelets from the site of their adhesion, unless many von Willebrand factors adhere to platelets and start applying the adhesive force on it. Also, you may notice that there are several different colors of these von Willebrand factor particles, the green ones and the purple ones. This stands for the phenomenon known as the mechanical activation of von Willebrand factor itself? Well, in fact, the structure, the multi-domain structure of this protein dictates some specific conditions under which it can bind platelets. It is known that it's well established for now that the A1 domains and A2 domains of this von Willebrand factor dimer in stagnant conditions, when there is no shear in the flow or when the force is lower than some known threshold, these domains can get coupled through the interaction, attractive interaction between these globular proteins. Therefore, A2 domain can block several specific amount of surface of A1 domain to prevent GP1B binding. When this protein is stretched by external forces, then GP1B can bind freely to A1 domain. This increases the affinity of platelets to this protein. In fact, we simulated this using a more detailed model. These three domains construct in high shear stress and in low shear stress, and we observed that indeed in low shear stress they stay combined together, and in high shear stress they have a tendency to decouple. This work has been recently submitted to one journal, and I will probably report in detail on another meeting. But we also included this into our model, and we found that the activation of von Willebrand factor is a multi-stage process. At first, when we only increase the shear stress from 0 to some intermediate value, we see that the elongation of von Willebrand factor happens. And only after several only increasing the shear stress up to a known threshold, the activation of each dimer happens. This is consistent with experimental observation by Fu and colleagues presented in Nature Communications. We compared and validated our model from these results and found the good sets of parameters. And basically, first, von Willebrand factor elongates in the shear flow. Secondly, the stretching forces cause the decoupling of A1 and A2 domains within this multimer, which increases the binding of GP1B platelet receptor. This turns us to the idea that the internal structure of each dimer of von Willebrand factor is quite important for its capability of binding platelets. It is important in terms of both the conformational changes in von Willebrand factor, its affinity with platelets, two platelets. So we decided to see in detail what's going on with this protein and how can we describe it in the model. Well, first, from the electronic microphotographs presented again in this work of Springer and other works, Joe, for example, we see that this von Willebrand factor has acquired this dimer of von Willebrand factor has a symmetric structure. First, we notice A1 domain. This one comes from a different dimer, probably. A1 domain is connected to D3 domain. Then there is a group of A2 and A3 domains, and there is a long stem which is not quite functional in terms of hemostasis, but is quite important, as it turns out, in terms of conformation of this protein. It starts with D4 domains, and then there are 6 almost identical C domains, which end up in the CT-CK ending. And it's symmetrical because the dimer is connected through this C terminal end to another dimer, and therefore it can form this shape which is known as the C-terminal bouquet or C-stem coupling. On a larger scale, the dimer adsorbed on some surface looks like this, not the dimer, the multimer, sorry, is like this, and we can see that this protein is very inhomogeneous along this line. There are some thinner regions, there are some aggregations of globular regions, and so on. So this structure, of course, is known to be important. It is sensitive to pH and salinity of the buffer fluid, and also is sensitive to hydrodynamic forces as we know it, and it seems to be important resolving the structure, the details of von Willebrand factor in the model to predict its functionality. So there is a need to create a more detailed model, and there we go to the part 2 of our work that I'm going to present today, domain resolving metascopic model of the von Willebrand factor. To make it short, basically we use the same method, coupling lattice-Boltzmann technique with particle dynamics. Here is the principal biological model, the structural model of the dimer of von Willebrand factor. Here is how we present it in the model. There are several specific types of bonded interactions, including bond angle conservation here and here, and also some stretching, specific stretching interaction imitated by Fene force here and here. We used the atomic force microscopy measurements of the stretching force of von Willebrand factor under such conditions that the experimentalists pulled the they attached by a special spring one of the beads to one of the ends of von Willebrand factor. They fixed the opposite end of the dimer of von Willebrand factor. They pulled this bead upwards and measured the force on the spring. Basically, we were able to reproduce it in the model, and we compare the force in the model with the experimental data. In these pictures, we see the two sets which correspond to different buffer pH level. And we see that the simulation data fits quite well the experimental data. The experiments are symbols, the simulations are lines, purple and green. Then we also compare to known simulation of multimer dynamics in plane shear flow. We also observe this threshold-like transition from collapsed to extended state for certain set of parameters in this model. And we also compare the multimer conformation for different parameterizations to known experimental results. In particular, we see that this second parameterization after equilibration of the protein is similar to this experimental observation at pH 7, and this one on the bottom is similar to this pH 6.2. In the first parameterization, it seemed a little bit too much, so therefore we were able to determine the correct set of parameters for domain-domain interactions. We studied the behavior of individual dimers in this model, especially thermal stability of this dimer in different parameterizations. We found out that the interaction between D4 domains is the main trigger that causes the conformation to change. We also simulated and measured from this simulation the radius of gyration of each dimer, depending on, of course, the number of dimers in the multimer. And the hydrodynamic radius also was measured for different parameterizations. And we indeed found out that D4-D4 interaction here is the main conformational switch for this particular protein. And it seems that any mutations in these domains, in D4 domain, may be quite important, quite influencing the mechanics of von Willebrand factor. Of course, this is still an ongoing work. Also, finally, I can present some dynamics of this multimer under extreme shear rate, 10 to the power of 4 inverse seconds, which is quite pathological, and it is known to cause undesirable transitions in von Willebrand factor multimers, especially the unfolding of A2 domain, which were indeed observed at high shear rate, and of course the separation of A1 and A2 domain, which increases the adhesivity to platelets. So therefore, I would like to conclude my speech. I would like to say that we show that the multiscale approach seems quite capable of reproducing specific features of microvascular thrombosis, and it seems quite promising within predicting the outcomes of mutations and disorders in platelets or von Willebrand factor or platelet rheology and so on. And after that, I would like to acknowledge the support from foundations, the acknowledged support of Computational Center at Moscow State University, and of course, would like to thank my colleagues and collaborators involved in this big project, and as well thank my students that worked partially on this project as well. Thank you so much for your attention.
Thank you very much, Alexei. It is very interesting talk. It was very interesting to listen it. Questions? Yes, please, Vitaly.
Yes, thank you, Alexei, for this indeed very interesting presentation. I think that, of course, we discussed many times before, but I think that I missed something in our previous discussion. When there is a wall damage because of injury and this platelet aggregation starts at this injury place, so what is the primary mechanism? Is it von Willebrand factor, how platelets attach to this injured wall, or it is collagen?
Well, basically, there are two different situations. I would like to go back in my presentation. For example, here we only imitate the inflammation, but not exactly the injury which exposes the collagen for the blood flow. In this case, of course, the endothelium cells do expose the von Willebrand factor from special granules inside them. But in the situations when we have a rupture of the vessel, of course, the collagen is the main trigger of everything, both coagulation and platelet attachment. And we now are studying the interaction between von Willebrand factor and the collagen itself to quantify it, first of all, from first principles from molecular dynamic studies, to introduce the adhesion of von Willebrand factor to collagen exposed blood flow. So it's
So it's von Willebrand factor from plasma and collagen on the wall, right? They interact, and then platelets come to attach to the von Willebrand factor, right?
Yeah, so von Willebrand is a kind of a mediator between collagen and platelets. Basically, platelets do have a receptor to interact with collagen directly, but apparently they are very short, and under shear rate, as we observe in microvessels, the longer ligands are needed, so von Willebrand factor comes to hand.
Well, and another question related to this is, again, maybe I forgot to miss something. Is there a direct interaction between von Willebrand factor and red blood cells?
I haven't heard about it.
So it does not exist.
Maybe it is, but I just can't recall any papers.
Okay, thank you again, and just not a question, but just a comment or something, well, more general question to think about. All this very interesting microscopic and mesoscopic study which you do. So I don't know whether it is possible, but it might be interesting to think whether it is possible to introduce it somehow in continuous models.
Vitaly, you just took my question. Just I wanted to ask.
Yeah. So sorry for that. So let us ask this question together, and
yes,
maybe Alexei can answer both of us.
To be honest, we started discussing this last week. How to implement the von Willebrand factor activation in continuous models. Of course, it's the next step that should be done. And there are several ways, for example, introducing a specific type of variable in the equation set that is von Willebrand factor concentration or activated von Willebrand factor and so on. Maybe we could also just implement it as changing the affinity of platelets or the rate of aggregation of platelets depending on local hemodynamic conditions and so on. Maybe there are some other schemes, and it basically depends on the model we are going going to implement.
Thank you very much. It was very interesting. Thanks.
Thank you too.
Thank you very much, Alexei. And now we proceed to the next speaker, Masalceva, yes?
Right.
Yes.
Dave.
Excuse me, I don't have your name.
Anastasia Masalceva.
Anastasia. Yes, please, Anastasia. The title of your talk, Initial Wall Shear Rate May Determine Microvascular Thrombus Occlusion Scenario. Please, Anastasia.
Can you see my screen?
Yes.
Oh, thank you. First of all, I would like to thank the organizers of the workshop for letting me present my work here today. The name of my presentation, I will recite it once again, is Initial Wall Shear Rate May Determine Microvascular Thrombus Occlusion Scenario. Here you can appreciate light microscopy imaging of normal thrombus formation in marine arterial. Thrombus size increases, here platelets are denoted by red, until eventually the thrombus begins to diminish in size. In pathophysiological scenario, the growth does not stop and leads to a blockage of the blood vessel, which we call occlusion. This condition may lead to hypoxia and necrosis, which are obviously highly undesirable. And but currently, the mechanisms of thrombus occlusion are not entirely clear. The question of what drives thrombus occlusion is widely approached with computational modeling. For example, the previous speaker, Alexei Belyaev, has previously developed a continuous model to address this question. In this model, thrombus formation took place in a segment of a microvessel embedded in a hydraulic circuit with a bypass. So the segment where the thrombus formation took place was imposed a constant pressure drop condition. So here you can see a section where a thrombus forms and a cross-section of this place. And the model suggested that increasing thrombus length relative to the vessel length or decreasing initial wall shear rate led to vessel occlusion. As you can see here, increasing the thrombus length or decreasing the initial wall shear rate. However, the continuous model does not allow us to study thrombus disassembly or embolization, and we only know if the thrombus growth would stop. So we aim to apply a previously developed particle-based model of thrombus formation to study whether for fixed relative thrombus length, decreasing initial wall shear rate would lead to thrombus occlusion. So our model is actually built in bottom-up manner and is rooted in experimental findings. The model considers a two-dimensional vessel, and platelets are explicitly modeled as discs. Platelets are brought in by the flow and attached to the injury site, which is located on the downside of the vessel and is represented by a layer of immobilized platelets. They interact with this layer by a primary interaction, bindings between GP1B receptor on platelets and the von Willebrand factor. This interaction is modeled via stochastic springs. So two platelets can switch between two states. They can be bound or unbound. When they are bound, and the switch occurs in a probabilistic manner. So when they're bound, the spring between the platelets gives rise to an elastic force and torque between these platelets, and it can also break, also probabilistically, and the platelets will go back to unbound state. So platelets accumulation and the interaction take place in a hydrodynamical environment. So the platelets are subject to hydrodynamical force, and to obtain velocity and pressure fields, we solve Navier-Stokes and continuity equations using open form in our computational domain. But geometry of the thrombus is not stable. New platelets attach all the time, and the geometry changes. So these fields should also change with time. And with this, we use a hydraulic circuit approach to for two reasons. First of all, it allows us to update boundary conditions when the thrombus geometry change in a straightforward manner. And also, it allows us to limit computations to a relatively small computational domain while maintaining a constant pressure drop condition on a vessel segment that has an adequate length. Physiologically adequate length. So to update inlet pressure and inlet velocity condition on the for the computational domain, we calculate the resistance of empty computational domain and computational domain with a growing thrombus. And we use this resistance to determine target pressure at the inlet using the ratio of the virtual part of the domain and computational domain. And using the ratio of the target pressure to current pressure, we determine new boundary condition for maximum inlet flow of the parabolic velocity profile of the inlet. So in this model, the length of thrombus changes all the time. So to compare it with the results of continuous model, we determine relative size of thrombus as the ratio of injury site to vessel length, the whole vessel. And this lambda is 0.047. So each time the thrombus geometry changes, we solve new problem using open form. So as I said, platelets interact with this injury site and with each other, but thrombus formation is majorly driven by platelet activation by soluble agonists. So in our model, we include soluble agonists, and we model them as virtual particles, thrombin and ADP. We model thrombin as a constant flow at the injury site, constant generation of these virtual particles. And these particles can activate platelets. So let me describe in more detail how we model these virtual particles. They are subject to Langevin equation, which we solve using velocity of the flow obtained in the hydrodynamical module. And they also diffuse in space. So we apply a diffusion member to this equation. The updated positions of these particles are transferred to the main part of the model to determine concentrations in in a rough spatial grid. And these concentrations converted from the number of particles in each grid element are used to determine the effect it would have on a platelet that would reside near this grid element. So the activation of platelets would result in the degranulation, which I will describe later, which will lead to appearance of ADP particles, and the process will repeat itself. It is divided into portions computationally, the one that is that takes place on CPU and the one that takes place on GPU, because we are talking about tens of thousands of virtual particles, and to accelerate these computations we use CUDA technologies. So let me go one slide back. As I already described, thrombin activates platelets, but what does activation mean? It means that mechanical parameters of the interactions change, and we have two types of platelet activation: the one that is default and I have described already, and the one that appears when platelets are activated. It mimics integrin interactions and is modeled with deterministic force field with Morse potential and platelets that elapse are elastically repulsed. So to model how soluble agonists change mechanical parameters of this interaction, we introduced a variable which we call extent of platelet activation, and probability of stochastic spin generation depends on the states of activation of two interacting platelets, and the magnitude of deterministic force depends on the state of activation of platelets. So as I have mentioned before, platelets also there is also a process of degranulation, which means that platelets release the dense granules, and we model this process because dense granules contain ADP, which is a major driver of thrombus shell formation. The cap on the thrombus. So all thrombin-activated platelets release the dense granules, and to model this process we use experimental data on dense granule secretion in response to different concentrations of thrombin, and all granules are released independently and stochastically. ADP particles that are released during degranulation bind to platelets, which we model using continuous kinetic equations, and this amount of bound ADP to platelets is directly related to its state of activation. So that is all on the model framework, and if you want to see details, please read our recently published article. Let's go to the results. So here you can I show you the typical time course of thrombus growth at a high initial wall shear rate. Platelets activated by thrombin are denoted here by blue, and platelets activated by ADP only by yellow, and the intersection is green. So you can see that the thrombus growth follows continuous cycles of platelet accumulation and rupture of the platelet aggregates. And here on a plot of thrombus height versus time, you can see how the height increases and then abruptly decreases. This is mean and S.М. for 3 stochastic simulations. And if we try to observe a thrombus under the same conditions, only the initial wall shear rate would be decreased 20 times. The mode of growth changes drastically, and instead of cycles of accumulation and disruptions, we see that thrombus grows until it comprises all of the vessel height. And you can see clearly that there are 2 regimes, and they're obviously regulated by initial wall shear rate. So why are we so sure that there was an occlusion and there was a full blockage of the vessel? So here you can see velocity profile for high initial wall shear rate, and you can see that intra-thrombus velocities are much lower than velocity of the flow in the lumen. And for the thrombus grown under low initial wall shear rate, you can see that intra-thrombus velocity is almost the same as the velocity in the lumen. So, and here you can see how velocity changes with the height, and in case of occlusion, it gradually falls down to 0, almost 0. So, if we take a look at the profile at the center of injury site and plot velocity in the vessel, you can see that in case we have a normal thrombus growth with continuous cycles of ruptures, there is a parabolic flow in the part of the vessel lumen that is not filled with thrombus. And in case we have a low shear rate, the vessel, the velocity is uniformly low in the whole vessel. And here you can see a close-up of this plot, and the interthrombus velocity for thrombus, for non-occlusive thrombus, is higher than the one for an occlusive thrombus, but the change is smaller than the difference in the initial wall shear rate. So we know that there are clearly 2 different regimes of thrombus growth, and we wanted to know when does this transition occur, the transition between 2 regimes. So we also calculated thrombus growth at 200 reverse seconds and 500 reverse seconds, in addition to 100 reverse second and 2000 reverse seconds. And here you can see that decreasing the initial wall shear rate, we move from green curve to red curve to blue curve to orange curve. So the height gradually rises and the amount of cycles of ruptures diminishes with the decrease in initial wall shear rate. And number, if we plot not height of the thrombus, but number of platelets in the thrombus, which correlates with this volume, you can see that though initial platelet accumulation rates increases with the increase in the initial wall shear rate. Eventually, as we decrease wall shear rate from 2,000 reverse seconds to 500 reverse seconds, we see an increase in the number of platelets. But increasing the wall shear rate further, we decrease the number of accumulated platelets, and eventually the number of platelets at 100 reverse second is as what would be expected with the linear accumulation of platelets in time. So here you can see quantification of these plots for different shear rates. This is height at after 90 seconds of thrombus growth for different shear rates, and this is initial platelet accumulation rate. There are clearly trends with an increase in the shear rate. So how does thrombus growth look like in this intermediate initial or shear rate values? Here you can see thrombus growth at 500 reverse seconds, and the thrombus grows until eventually it embolizes, and a large part of the platelet aggregate disrupts from the main aggregate. And here you can see thrombus growth at 200 reverse seconds, and it reminds us of how thrombus grows at 100 reverse seconds, and with time it almost occludes all of the vessel by the 90 seconds of simulation. So it is expected that with more time the vessel would be occluded. So to make some conclusions from my talk, first, in our particle-based model, thrombus growth has two regimes, that is occlusive growth at low initial wall shear rates and non-occlusive repetitive cycles of assembly and embolization at high shear rates. And the transition between these two regimes occurs somewhere between 200 and 500 reverse seconds initial wall shear rate, which is in line with our prediction if we take into account the continuous model of thrombus growth. Only here we don't see that that thrombus growth stops. We rather see that it limits its growth by continuously embolizing. I would like to thank my colleagues that helped in the development of this model, and thank you for for your attention. And I'm ready to answer your questions if you have some.
Thank you, Anastasia, for the interesting talk. Anas Bushnita want to ask a question. Please, Anas.
Yes, thank you very much for this very interesting talk. So I was wondering, I saw that your model accounts for heterogeneity of platelet size, which means that you have big platelets and smaller platelets. So I was wondering if you have studied the effect of platelet size on these different regimes or on the dynamics of thrombus growth. And I'm asking this question because, you know, in COVID-19, there is this thrombocytopenia, which means that patients have a lack of platelets. They have low concentration of platelets, but at the same time, their platelets, they have a higher incidence of thrombi. So one explanation for that is that they have bigger platelets.
Thank you very much for this question. In the model, the platelets are heterogeneous in accordance with experimental data on platelet size distribution, but that's normal platelet size distribution, and it would be indeed really interesting to study how the model would act for patients with thrombocytopenia. But we haven't done that, and that is a nice idea. Thank you.
Thank you.
Okay, other questions? Yes, Vitaly?
Yes, thank you, Anastasia, for nice presentation. These simulations you have done, what is the vessel diameter there?
Vessel diameter is 35 micron.
So you give here these two regimes and the transition between two regimes. Are there experimental estimates for this transition between these two regimes? For such vessels?
Actually, I don't know of any experimental studies that would study thrombus growth at different wall shear rates, because it is really hard to assess wall shear rate in a real vessel. And
there are experiments in these flow chambers, for example.
Yes, yeah. microfluidic chambers. Yes.
Yeah, we haven't compared the results of the model to microfluidic chambers.
Yes, in fact, of course, I am familiar with this works, but just listening to you, I realize that I don't remember. Maybe Anas can help us because I think there are some experimental data, but I don't remember clinical or, sorry, not clinical, but mice experiment or flow chambers. Anas, do you remember this? Because Anas uses some comparison with experimental results. I don't remember exactly.
Yes, I think there are some existing benchmarks. There is one for venous thrombus formation, but for arterial ones, I think there are some others, and I think maybe Alexei knows some of them. But I also know some of them. Yes.
Well, please, Anas, if you can send us, not maybe not us, but maybe Anastasia, or send me, and I will send to Anastasia this works where they present these experimental results on vessel occlusion. I think it can be useful to compare these numerical simulations.
Yes, that's great.
Okay.
Other questions?
Well, I don't know if no other people, I can continue with some other questions because it's a rare case when we have some time to discuss.
Yes, very rare.
Because usually we want to keep the schedule, so we have 10 minutes before or 9 minutes before the next talk, so we have some time for the discussion. So Anastasia, again, though I'm familiar with this work, but maybe I forgot, could you explain please how you model blood flow, flow velocity? Is it Navier-Stokes equations or some simplified model?
Yeah, it's Navier-Stokes equations, but in a quasi-stationary approximation. So the flow changes stepwise at some small, actually, time intervals comparable to attachment of a single platelet.
Mm-hmm.
And why do you use two-dimensional simulation? Why it is sufficient?
Well, that is a good question. Actually, we use two-dimensional approximation because this reduces computational complexity greatly. And to calculate such a model in even a two-dimensional approximation, we need roughly a week for 90 seconds on a supercomputer. And but we are currently developing three-dimensional extensions of this model, and probably my colleagues will share some results in the near future.
But why it is so long? How it's you don't have so many particles? Well, you have probably several hundred platelets. Why it takes so much time to compute this?
Because we have several stochastic processes, like interaction, primary interaction between GP1B receptor and von Willebrand factor. It is stochastic, and platelet degranulation is stochastic, and of course some large part of this time goes to open form solutions of computational fluid dynamics.
Okay. And also another interesting question, as far as I remember, it's about indeed the stochasticity. As far as I remember, some of our previous discussions, this stochasticity in platelet aggregation, in fact, plays some role and changes some behavior, right, of this thrombus growth.
Right. Stochasticity is important for thrombus growth.
Could you explain what indeed happens due to this stochasticity?
So due to this stochasticity, we can see some fluidity of the platelet aggregate. If all force was deterministic, we would see just a rigid aggregate. And for physiological thrombi, it is very important that it has some ability to move, to flow.
Yes, okay, thanks. Well, to summarize my questions, I would say that it's a very nice work, and there are also some further questions on further development of this model, which you could take into account. In particular, as far as I understand, thrombin is just diffuses from the wall, so you don't take into account thrombin production in plasma, for example, no?
No.
Or activated platelets also express thrombin, prothrombin, things like that. So you can, in principle, add these additional factors in the model, and I think it will be also interesting to see how all this works together. Thank you very much. It was a nice work and a nice presentation.
Thank you very much for valuable comments, Vitaly and Anas.
And I have one more remark regarding conclusions which may be derived from the two-dimensional simulation, how they may be connected, related to the three-dimensional experiments. I mean experiments, physical experiments in microfluidic chambers. The point is that hydrodynamic forces which act on the thrombus is proportional, roughly speaking, to the surface of this thrombus. But in a two-dimensional case, it is proportional to the perimeter. And the force between elements of this heap, it is a function of distance. And it means that hydrodynamic force in three-dimensional case is has more impact, more effect to the thrombus. And that's why it is interesting. Is it possible to put a bridge between 2D and 3D? Or this should be two different, absolutely different simulations?
Well, we try to take into account how force would affect a three-dimensional platelet. We embed it in how we calculate the Stokes force in the model. Yeah, in three-dimensional force, we would three-dimensional thrombus. We would also have a different packing of platelets. So the and flow would have more bypasses to go around platelets. So the intrathrombus velocities would increase, and I can say right now how the conclusions would change for a three-dimensional model.
Okay, thank you.
Thank you.
If no other questions, maybe we shall ask Eugene Bershadsky, yes?
Yefim Bershadsky.
Yefim Bershadsky to open his presentation, and in 1 minute you can start.
Can you see my slides?
Yes. Yes, and please remove the bottom message. Just click to yes here. Yes. Okay.
Oh, I can start. Yes.
I think let's wait 1 minute more.
Okay. Okay. Can I start now?
Yes, Yefim, please, please go ahead.
Hello, everyone. My name is Yefim Bershadsky. I work in the Center for Theoretical Problems of Physico-Chemical Pharmacology of Russian Academy of Sciences. And my work is devoted to analyzing the process of thrombus embolization under arterial shear rate conditions using particle-based model developed by Lera Kaneva. First, let's look what is embolization. Embolization is a process that occurs in different animal models, and sometimes it occurs also in humans. It's when some piece of the thrombus detached from it. It may happen by different reasons, but first let's look at the video, which shows how it works. This video was kindly promoted by Alexandra Yakusheva. It shows how thrombus grow in mouse carotid artery. This is ferrum floor-3 injury thrombosis model. So part of the vessel is exposed to ferrum floor-3 injury, and it is thrombogenic situation, which triggers the thrombus growth. So let's see what happens. You just seen the embolization event. It's when this huge part of thrombus disappeared. Let's look again. So that's it. It also considered that embolization may occur when thrombi grow in human coronary arteries. So this is the event which may be part of acute coronary syndrome. And I think everyone understands that it's very important to understand how it works and why embolization happens or doesn't happen. If it doesn't happen, then the occlusion of the artery may occur, and it will cause very bad events for people. So my general aim is understanding factors that affect thrombus embolization in vivo and in vitro, and my special goal is to elucidate the critical parameters that determine thrombus stability against the flow using the particle-based model. This model is pretty similar to the model which was just described by Anastasia Masalceva. She helped me very much, and I hope it will be clear for everyone now. Look, at the right upper angle, you may see the simplest scheme of this model. It is a 2D model which represents vessel as a rectangular with sizes 35 and 200 microns. Platelets are represented as circles. Here you can see these gray circles. which attach to one another. Injury site is this black line, and it is in model, it's presented as anchored platelets. These are platelets which don't move and don't obey to Newton's equations and Newton's laws. But usually other platelets obey to Newton's laws. Platelets have a real and hydrodynamical radii, which means that on this figure you may see that they are gray and they contact each other. It is their real radii, but hydrodynamical radii is less. It's important for our model because if hydrodynamical radius will be equal to the real radius, there will be no flow inside the thrombus at all. So we solve it by such a trick. Model has two basic models, hydrodynamical model and platelet dynamics model. Hydrodynamical model generates the mesh in the vessel and in the thrombus, and then solves stationary Navier-Stokes equations using open-form software. And platelet model computes interplatelet forces and dynamics of platelets using Newton's equations. Let's dip a bit deeper in the model workflow. So you may see on this slide how these two models work. On each time step, first, hydrodynamical model builds mesh in the vessel and inside the thrombus. This mesh depends on the current positions of platelets. Also, it solves Navier-Stokes equations and gets hydrodynamical forces acting on platelets. These forces then are used by platelet dynamics model. Platelet dynamics model computes interplatelet forces and total forces acting on each platelet, and then it solves Newtonian equations and finds new position of platelets. And at the next step, everything repeats. So this is general workflow of the model. And on the right figure, you may see how the mesh looks. You may see a rough mesh in the vessel and a pretty fine mesh inside the thrombus. And here you may see hydrodynamical radius, hydrodynamical radii of platelets. These little white circles are platelets. They are, when we build mesh, they are considered impermeable and no slip condition is applied on their surface. Also on this figure, you may see velocities in the vessel and in the thrombus. Usually velocities in the vessel are, say, 10 times higher than velocities in the thrombus. Actually, it means that our thrombi are very permeable. And I have additional data that their permeability may be estimated as 10 in the power of minus 12 square meters. So actually, it's a bit more than you would expect in a real thrombi. I have my own estimates. Then in realistic thrombi, you should have 10 times less permeability. So Anastasia told you a lot about forces which are used in this model. And actually, my model used the same forces as hers. The main force which acts is deterministic integrin force, represented by Morse potential. You may see it on the right figure under figure E. It's a potential well type force, so it's very short range and very sensitive to the thrombus packing density, which is important. Also, we have von Willebrand mediated force represented by stochastic springs. I will not talk about it much because it is not very important for the thrombus embolization because it's pretty slow, because it's pretty low according to the integrin force. Also, we have elastic repulsion between platelets when they are too close to one another, a platelet wall repulsion, and hydrodynamical Stokes force acting on platelets. This force is also very important for thrombus embolization. We process result using Python model, and processing gives us a lot of information. Actually, we know everything which happens in our model. We know inlet flows, inlet velocities, forces in thrombus, how thrombus geometry changes, and we can analyze embolization events. And on the right figure, you may see our typical figure. Yes, excuse me for such word combination. So on the right figure, you may see a mean hydrodynamical force in thrombus and how it depends on thrombus height. On the x-axis, there is thrombus height, and on the y-axis there is force measured in piconewtons, mean hemodynamical force in thrombus. And you may see that this line is very steep, and when thrombus height achieves vessel diameter, which is 35 microns, it increases, I think, maybe 30 or 40 times relative to the situation when thrombus height is only 9 microns. So it's very steep, and it's very important for thrombus embolization. About our simulation protocol. So my current goal is analysis of mechanical stability of homogeneous thrombus with platelets having constant level of activation. This three snapshots shows our thrombi at 3 time moments. First upper snapshot is the snapshot which I create myself with our Python model when I fill the given shape with densely packed platelets. You may see that they are very densely packed. It's not physical, but when we start the flow on the second step, platelets start to interact according to the Newton's equations, and new packing density appears, and thrombus gets shape, which is shown on the second snapshot, which is pretty good. Also, at the first step, we perform the simulation during 6 seconds, and thrombi are either embolized or not. If they embolize, they will look somehow like you may see on the first snapshot. On this video, you may see actually a typical simulation. This thrombus did not embolize. So after the first second, nothing happened. It was pretty stable. And there is nothing interesting to look at. But let's look at another video with embolization. It's very interesting. So let's look at snapshots. First, thrombus start to move, and you may see that some piece from the downstream side of the thrombus, because flow is from left to right, and some piece from the downstream side start to detach. Then it detach, and then nothing happens. So it was really interesting to see that this thrombus is not that much bigger than the previous one, just several, maybe 10% bigger. But it embolizes, and the previous thrombus didn't embolize. And we were very interested in what is the difference. Is there really a big difference between these two thrombi? And trying to answer this question, we started to build such figures. Let's talk about such figures, what they show. So each figure shows what happened with one thrombus during such simulation, which I told you before. So each thrombi either embolized or not. On the left figure, we had a series of 30 thrombi with different height, but with the same length equal to 100 microns. And when thrombus height was less than 26 microns, all these thrombi were stable. But when it was higher than 26 microns, all of them embolized. So thrombus height appears to be a key parameter which determines thrombus fate. I should mention that thrombus height was measured at 100 milliseconds after simulation was started. So it is just the initial thrombus height when it was still stable. And on the right figure, you may see the same graph, but for thrombus length 50 microns. So these were shorter thrombi. And there is also a great importance of thrombus height, but you must see that there is some stochastic variability. So some, for a given height, some thrombi embolize and some don't. But actually embolization starts earlier when thrombus height equal to 21.4 microns. So I conclude that basically thrombus height is a key parameter which describes, which determines its fate, but also thrombus length is also important, and longer thrombi tend to be more stable. Also, we get such a figure which depicts how total hydrodynamical force acting on thrombus depends on thrombus height. So on the x-axis, there is thrombus height at 100 milliseconds after the simulation was started. And on the y-axis, you may see a total hydrodynamical force acting on thrombus also at 100 milliseconds after the simulation was started. So the initial moment. And you may see that it's a very steep line. And when when this force achieves some critical value over 3,000 piconewtons, thrombi embolize. So this force is critical determinant of thrombus fate, and when it changes with thrombus height, and that's why thrombi embolize. And I want to say that here a few words that it is not surface force. It is not that force that acting on the surface of platelet of thrombus, but actually it's a volume force. So I can't show this data, but surface force is pretty small compared to the volume force. So flow inside the thrombus in our model, it's very important for the thrombus embolization. Also, we measured extent of embolization. This term is what percent of thrombus mass detached. So if 10% of thrombus mass detached, we say that extent of embolization equals 10%. And you may see that in our simulations, it varies from 20 to 60% and does not depend on thrombus height. So it's quite stochastic process. And we were very interested in what happens, why different thrombi embolize differently. What are these parameters? Because yes, thrombus height is really important, but maybe there are some other parameters which influence this process. And actually there are some other parameters. And first we started with analyzing the embolization piece. So look at this figure on the down part of the picture of the slide. You may see this white platelets are the platelets which actually detached. So this white piece is the piece that embolized, and red platelets didn't detach. And this black line is the line which starts at the central part of the thrombus. And you may see that actually the piece that detached lies downstream of the thrombus. It is not symmetrical at all. And it looks actually like some piece starting from the right down angle. And then if you draw the line maybe 20 degrees, line with angle 20 degrees, you will see how this piece looks. And on the right upper figure, you may see statistical data. Each point is the number of platelets detached in the downstream, which lie on the downstream side and on the upstream side of the thrombus. For example, here you may see, I think, over 150 platelets on the downstream side and over maybe 20 or 30 platelets on the upstream side of the thrombus. So there is really asymmetrical embolization, and we tried to analyze this process. And we asked ourselves, can we predict the fate of a given thrombus using measuring the mechanical forces inside it? And we introduced such a concept as the concept of embolizing potential, which I try to explain you in details. So on the left upper figure, you may see how force balance in the thrombus looks. Look at this gray piece and let's count forces acting on it. So there is hydrodynamical forces, which is applied maybe somewhere in the center of piece, and it equals sum of hydrodynamical forces acting on each platelet in this piece. And second force is integrin force. Integrin force is sum of integrin forces acting on the surface of contact between piece and the rest of the thrombus. So integrin force is counted as bulk integrin force is sum of integrin forces between white and red platelets on this down figure. I hope it was clear what I'm talking about. It's the force that keeps this white piece of thrombus from detaching. So it keeps it, and hemodynamical force pulls it away. And their balance determine whether this piece will embolize or not. And here is the concept of embolizing potential. On the right upper figure, you may see that for each piece, I determine relation, which can be called just potential, and it equals to relation between pulling force and integrin force, acting on some gray piece, yes? And each angle starts with vertex in the upper down angle of the thrombus, determines some gray piece, let's call it gray piece, determines some piece, and we can measure potential for each one. And then we can find maximal value. And the graph at the right down angle shows how this potential depends on angle. And for this graph, embolizing potential will equal 1.14 and will be achieved at the angle of 0.38 radian. So it's, I don't know how much, it's maybe 20 or 30 degrees. So if embolizing potential is higher than 1, then thrombus should embolize. If it is very less, it's maybe 0.1 or 0.2, then we should be sure that thrombus should not embolize because pulling forces are too low to detach pieces. And we have statistics on this slide which show that when embolizing potential is higher than 0.3, then all our thrombi embolize. And when it's less than 0.2, then no thrombi embolize. And in some middle zone, only 2 thrombi did not embolize and other embolized. So it seems to be a very good predictor of thrombus fate. And it's important that it's dimensionless value. It just compares intrathrombus mechanics with hydrodynamical forces acting on thrombus. So actually, it can be calculated for any thrombus, and it's intriguing think whether it really works and whether it really able to predict the fate of any thrombus in any vessel in humans. Actually, I don't know the answer because we currently don't have such data which can help us answer this question. But it should work because it's based on simple physical laws. And my conclusions. I conclude that thrombus height is key parameter which determines whether the homogeneous thrombus will embolize or not. Also, I see that hydrodynamic forces increase rapidly when thrombus height increase. I see that long thrombi are more stable than short ones, that thrombus embolized mostly on their downstream part, and I hope that embolizing potential is a good predictor of thrombus fate. I should say that all these conditions are based on in silico experiments with small homogeneous thrombi, but I hope that they will work for really any thrombi due to the physical nature of embolization process. I want to thank my academic advisor Dmitry Nichipurenko for his ideas, discussions, and critics. Also, I want to thank Lera Kaneva, who developed the model I use, for her help in understanding how her model works. And I want to thank Fedor Balagin for technical support because we solve all these equations on server. Server does that work good, and sometimes it breaks up, and Fedor always helped me to make it work. Thank you for your attention.
Thank you, Efim, for the interesting report. Questions, please. Yes, Vitaly. Please.
Well, can I? Well, traditionally, I will ask some questions. Okay, thank you. It was also a nice work, and I enjoyed it. And now I think I understand better why it takes so much time for the simulations, because in fact you have a very complex domain, right? You consider each particular platelet, right, as in your simulation. In the Navier-Stokes equations, you have a very complex domain with each particular platelet considered as a boundary of the domain, right?
Yes, yes. Mesh in thrombus is very complicated.
Yes, and you recalculated every time step. It's really a huge. It's really a huge work for your computer to do.
Yes.
Because
but
usually
we can't do it any other way, because we should know flows inside the thrombus. So these flows are critical for the thrombus fate.
Yeah, for such a detailed analysis, yes, maybe. For more detailed analysis, we use, of course, much simpler flow models inside the thrombus, like a flow deceleration, like something like a porous medium. But okay.
Yes, porous medium Camsol model. I worked with it, and it's really pretty good for such things.
Okay. But yes, I understand your idea and how you find these pieces which can detach, and it looks like that it works nicely. But I have some questions to it. In particular, you say that longer thrombi are more stable. I did not see it from your construction. Why it should be more stable? In fact.
Yes, I'll explain it. Just let's go to this slide. Okay, I have some additional Camsol data which I can show here, but I see that the flows inside the long thrombi are less. So flow velocities inside the long thrombi are less than flow velocities inside the short ones. It's due to the fact that long thrombi have higher resistance, hydrodynamic resistance.
Yeah, if you take the whole thrombi, but inside, even if flow velocity is less, but the thrombus itself is longer, so the overall force can be also higher because the thrombus is longer.
Yes,
so
yes, you're absolutely right.
It's difficult to say.
Yes, you're absolutely right. Total force is proportional to thrombus length, but also there is integrin force, which is also proportional to thrombus length.
No, sorry.
So
if you take vertical cross section, so it's a local force. It does not depend on the length of the thrombus.
No. Look at this white piece. Yes. So you may see that if this thrombus will be twice twice length as this one, yes, this white piece will be twice. So there will be twice more platelets in it. Yes. Right. And actually, this integrin force will also be twice more because.
Sorry. No. You take the length of this interface will be twice more, but the volume of this white part will be more than twice more. Okay. No, it's also twice more. Or it's difficult to say because it's length and height which change at the same time. So force can change it, in fact, more than twice. So it's really not simple. Of course, you present the results. If you show that your simulation shows that this is like that, okay, we accept that. But the explanation may be not so obvious because the relation between this volume of this white piece and the surface of this white piece, so how it changes depending on the thrombus length, it's not quite obvious for me.
Actually, I think that volume to surface does not change when the height is the same.
But it is not the same.
It's
because it will grow. It will grow for if the thrombus is longer. I think its height will be also larger.
We compare just thrombus of the given height. So
okay.
For the given height, we may say that actually thrombus length will not affect the volume to surface relation. Yes, and then flow velocity inside the thrombus will be the key parameter for the embolization.
Okay. Also, I think it might be interesting to see the force distribution. Did not you do it?
Force distribution,
the force distribution
inside
inside
the thrombus.
the thrombus, right?
I think that it is associated with velocity distribution, and I have this slide from Anastasia Masalceva.
No, it's not. It's not only velocity, because flow velocity gives the force at one point. But if you take a platelet inside, so it is pulled by the neighboring platelets, you see, so it will be the interaction of flow of this resistance force to flow and all the pulling forces from other platelets.
But you ask about hydrodynamical forces or
no, about forces acting on each platelet.
Total force. Okay, I don't have such a figure. So this is figure only I have from Masalceva work, which shows flows inside it.
Yeah. So it can be really useful to understand what happens if you, for each platelet, if you present the force acting.
Okay, you are right. It would be very interesting to look at real forces, how they work in vitro.
Yeah.
Yes, yes, it's interesting.
Yes, how they are distributed inside thrombus, and it will help you to understand why this clot rupture occurs in some particular places. Okay, anyway, I stop with my questions. It's a nice book. Thanks.
Yes, okay. If no other questions, actually we have quite fruitful discussion. We had. Okay, if no questions, let us thank him again, and we shall proceed to the next speaker, Tatiana Salikhova. The title of the talk, Modeling of Shear-Induced Platelet Activation in Patient-Specific Arteriovenous Fistula for Hemodialysis.
Good evening. Are you hearing me?
Yes.
And do you see the screen?
Yes.
Yes? Okay.
Yes, you can make full screen. Yes, perfect.
I can start or we'll wait?
Yes, you can. We can start at 5.
We can start.
Yes.
Good evening, dear colleagues. Thank you for the opportunity to take a talk. I'd like to present a talk, Modeling of Shear-Induced Platelet Activation in Patient-Specific Arteriovenous Fistula for Hemodialysis. Let's start with the explanation. It is known that hemodialysis is a prevalent method for replacement therapy in patients with end-stage chronic renal failure. The total number of patients requiring hemodialysis is growing steadily every year. The duration and the life of these patients on hemodialysis directly depend on the reliability of vascular access, which must provide adequate blood flow and function for a long time. Arteriovenous fistula, it is the most preferred option for this permanent vascular access for hemodialysis. Arteriovenous fistula, it is a surgically created connection between the patient's artery and vein. You can see in screen here with the artery of the patient. It is red and blue. It is the vein of the patient. And arteriovenous fistula, it is a connection between the artery and the vein of the patient. Then the blood goes to the dialysis machine to pure the blood, and then blood goes back to the vein from the dialysis machine, pure blood to the vein of the patient. This connection is known as arteriovenous fistula. But after the creation of arteriovenous fistula, the flow through the fistula vein significantly exceeds its preoperative value. Such hemodynamics in AVF leads to the development of local disorders of hemostasis that are not detectable by common tests designed to detect systemic disorders of the hemostasis systems. In such system, high shear stresses conditions in a way exist, and that may lead to the platelet activation and subsequent thrombus formation and embolization. And elucidation of the role of patient-specific hemodynamic factors in the occurrence of thrombotic complications remains an urgent task of modern hemodialysis. In this talk, I'd like to discuss the application of our computational approach to the assessment of the level of shear-induced platelet activation in patient-specific arteriovenous fistulas. The calculations took into account information on the arteriovenous fistula vessel geometry, blood flow intensity, and the size of von Willebrand factor multimers. In the first step, the patient undergoes a radiological examination procedure, and immediate result is a series of images containing information about the anatomical structure of the vessels at different depths. It calls a step of slices. Then on the next step, it is B, we reconstruct the geometry of the vessels by isolating the lumen of the vessels. This process is called segmentation at its slice, and then we triangulate their inner surface. The resulting surface mesh reproduces all anatomical structures, all features of the vessels of interest. Then we generate the volume mesh. After this, we go to the calculations. We use our mathematical models. We used CFD approaches, computational fluid dynamics approaches, and our model of shear-induced platelet activation. Then we can here we can take into account, for example, arteriovenous fistula flow profiles or information about, for example, the size of von Willebrand factor multimers. And then we, at the last stage, we prepare the video of our calculations, and we can plot different graphs to see the influence of different parameters on the level of shear-induced platelet activation. The analysis of shear-induced platelet activation was performed on two major arteriovenous fistulas of the patient. On the left, you can see the fistula of the first patient. It was formed in the forearm on the non-dominant upper limb of the patient from the radial artery, and the cephalic vein of the patient. That's why this fistula is called radiocephalic fistula. The second fistula, it is on the right of the slide, was created at the elbow of the non-dominant arm of the brachial artery and the cephalic vein. That's why it's called brachiocephalic arteriovenous fistula. These patients were subjected to non-contrast enhanced magnetic resonance angiography on the non-dominant arm vessels. You can see that blood flow goes through the proximal artery, and then it goes to the distal artery and to the vein. In both fistulas, the same. Let's go to the shear-induced platelet activation. Let's take a look about this mechanism. It is known that thrombus formation in large arteries can be initiated by signaling pathways induced by shear. Platelets play a key role in this arterial thrombosis due to their ability to be activated under dynamic shear stress. Both of the amplitude and the duration of shear stress determine whether the platelets are activated after passing through this high shear stress zone. One of the characteristics of the shear action on platelets under unsteady shear stress conditions, it is the cumulative shear stress, KSS. It is the variable that can be defined as the integral of the shear stress along the platelet trajectory, which pass through the high shear stress zone. Tau, it is shear stress, KSS cumulative shear stress, and T out means T in. It is time period of shear stress action under critical value. And if the cumulative shear stress exceeds a critical value, KSS not 0, shear-induced platelet activation can be initiated. It was recently suggested that the critical value of cumulative shear stress depends on the size of the von Willebrand factor multimer, and this is the number of monomer units in the multimer von Willebrand factor. And the aim of this work was to analyze shear-induced platelet activation in two patient-specific fistulas. It was assumed that the unfolding of von Willebrand factor can be that von Willebrand factor can unfold under overcritical cumulative shear stresses, and subsequent binding of von Willebrand factor multimers with platelet GP1B receptors trigger outside-in signaling and leads to the platelet priming. And platelet priming leads to the platelet activation, which leads further functional reactions in platelets. And the goal of this research was to analyze how aware flow rate and the von Willebrand multimer size influence on the level of shear-induced platelet activation. Let's take a look on the mathematical approach. On the first step, we solve unsteady Navier-Stokes equations using finite volume method in the packet open form. As a result, the distribution of the velocity and static pressure in fistula were obtained. Further, the shear rate tensor were reconstructed using this velocity field. And then the magnitude of this tensor was found using two formulas, formula number 3 and formula number 4. It is a well-known approach. Blood was considered as incompressible Newtonian fluid. Dynamic viscosity was calculated from a well-established relationship with the hematocrit of the patient, which we know from our doctors. A time-dependent Poisson velocity profile was set at the artery inlet and the outlet. The average speed, the instantaneous average speed was calculated based on the volumetric flow, which was set at the inlet and inlet boundaries. Volumetric flow waveforms over time have been adapted from the literature from the group Inner Ear Dutcher et al. At the outlet of the vein, the static pressure remained fixed and the velocity was allowed to float. No sleep conditions was prescribed on the wall of the vessels. It is about the boundary conditions. Then we have the distribution of shear stress, and we use the distribution for the calculation of the cumulative shear stress in our investigated geometry. You can see equation number 5, which we use for the calculation of cumulative shear stress. Tau with tau, we call this tau ds. Tau ds depends on von Willebrand factor multimer size. It denotes the threshold value of the shear stress for the von Willebrand factor multimers with given number of monomers. This means that the cumulative this dependence was obtained in our previous work, and in formula 6 you can see the approximation when the number of monomers is more than 1. It is the approximation form for this tau ds. In this equation, the cumulative shear stress was 0 at the inlet to the proximal artery, and the outlet from the artery and vein, zero gradient conditions was established. A resultant distribution of cumulative shear stress was used to calculate the level of priming and platelet activation of platelets. First, we solved the equation for the concentration of resting or non-activated and activated platelets. And the distribution of after calculating the concentration of non-activated platelets or resting, we calculate the distribution for activated platelets using the equation 8, where P at P0 is the initial concentration of resting platelets as usual, and CSC0 it is also the function of multimer von Willebrand factor multimer size, and it is denotes the threshold cumulative shear stress for the unfolding of such multimers. And simply the approximation when the n more than 1 is given by the formula 9. And the last, it is the calculation of platelet activation level. It is a measure of platelet activation in our model. It is the fraction or level or percent of activated platelets averaged over the cardiac cycle at the outlet of the vessel under conditions that we use. And this formula we use for the estimation of platelet activation level, for the estimation of shear-induced platelet activation in our geometry. Let's go to the results, to the application of our developed approach. Next, we use our approach for the estimation of shear-induced platelet activation, and we determine how it depends on the fistula flow rate and the von Willebrand multimer size. On this side, you can see the results for the patient 1. And for the biggest values of the volume flow rate, it is 725 milliliters per minute, and the multimer number 100. It is known that according to clinical studies, this value vary from 300 to 100 milliliters per minute in successfully matured radiocephalic fistula. And you can see the distribution of velocity. It is the first column that it goes the shear stress, then cumulative shear stress, and platelet and concentration of activated platelets. The first line, it is the systole, and the second line, it is diastole. Here we can see that red color, it is the maximum, it is the big concentration of some variable or big value of some variable, and blue, it is the less value. We can see that the flow inside fistula is such difficult. The calculated streamline behavior has a complex nature through this cardiac cycle, and this means that such observed flow instability further indicates that both amplitude and the duration of shear stress should be considered when we assess the effect of blood flow on the platelet activations. Those of overcritical shear stresses and cumulative shear stresses, we can see that they are near the proximal part of the artery wall and the outer wall of the fistula vein. The presence of these zones caused platelet priming or platelet activation in the fistula vein through all entire cardiac cycle, and the CPACT level for such case did not exceed 2%. For the second arteriovenous fistula, we have the same pictures, and the behavior of streamline during this cardiac cycle was qualitatively the same as the arteriovenous fistula for the first patients. But there the shear-induced platelet activation level did not exceed 0.2%. That means that activation in such fistula is more or less than in previous one. Here you can see the animation video for primed or activated platelets into patient-specific fistulas. We can see the distribution of these platelets for different multimers, for different sizes of von Willebrand factor multimers, for N10 and N100. First, we can see that activation in the first fistula is greater than for the second, and different concentrations of primed platelets are in between different multimers among one fistula. Let's go to the numbers, to the CPACT level of plate, to the CPACT level in both arteriovenous fistula. We can see at this slide the dependence of CPACT level on arteriovenous fistula flow rate. On the left, you can see the results for the first fistula. We can see that at flow rate QI, we have the same CPACT level for both multimers, for both von Willebrand multimers. That means that when flow is less than QI, the greater CPACT level is for the highest multimers. And when the flow is greater than QI, the trend is opposite. The level of platelet activation for the smaller multimers is higher than for the large multimers. For the second arteriovenous fistula situation is different. Here we cannot see the QI. Here the activation for greater multimer numbers is greater, and the activation with the growing flow rate is more and more, is greater. Yes, we can see this. Here we can see critical flows. They marked by green, Q critical for different multimers. Q critical, it is Z flow, lower which shear-induced platelet activation is absent. We can see that for both arteriovenous fistula, Q critical is less for greater von Willebrand factor multimers than for the little ones. Let's go to the next slide. This is connected with the dependence of the CPACT level on von Willebrand subunits, on the number of von Willebrand subunits. For the first patient, we can see that when the flow is 300 milliliters per minute, it is the growing function of N. And for the flow, for the greater flow, it is the decreasing function with N. This suggests that the decreasing of von Willebrand size may lead to an increase in shear-induced platelet activation at sufficiently high flow rates through arteriovenous fistula in patient 1. The dependence of the CPACT level on von Willebrand size multimer in the second patient was also determined on the right side. But their flows are greater than in the previous one. And the CPACT level increased with increasing von Willebrand multimer size for all considered flow rates in this arteriovenous fistula. Then for both patients, we obtained a shear-induced platelet activation parametric diagram. For how we built them. We found critical flow rate for every multimer size. You can see them as points on these graphs, and that's why we have the line which distinguish two areas of the parameters in our diagram. The first area, marked number 1 with green, corresponds to the parameter values at which no shear-induced platelet activation observed. It is area 1. In turn, the second area, which lies above this curve, the second area is the range of parameters where the shear-induced platelet activation should occur. We can see there that for both patients, the critical flow decreases monotonically with increasing von Willebrand multimer size. I'd like to note that for the effective hemodialysis, flow through the arteriovenous fistula should be no less than 300 milliliters per minute to maintain effective hemodialysis. And we can see that for patient 1, the critical flow rates were significantly lower than this above value. This suggests that in this case, shear-induced platelet activation should take place in all practically important flow range in this patient. In contrast, for the second patient, we can see that shear-induced platelet activation level remains 0 up to flow rates of approximately 700 for N10 and 400 for N100. It can be concluded that shear-induced platelet activation is not the risk factor for this patient up to the certain critical value of the flow rate through the arteriovenous fistula. And let's go to the results. In this work, we obtained the dependencies of shear-induced platelet activation on the arteriovenous fistula flow rate and von Willebrand multimer size. It was found that shear-induced platelet activation was not observed at below the arteriovenous fistula critical values. The CPACT level was greater for larger multimers at low flow rates, and the opposite trend was observed at high AV flow rates for the patient 1. And for the second patient, the larger von Willebrand multimer size was the higher the CPACT level. In the second patient, CPACT level may be completely absent within the physiological range of the values of von Willebrand multimer size at flows which is sufficient for hemodialysis. And in the first patient, shear-induced platelet activation should be initiated within all practically important range of flow rates. The CPACT level was greater for larger AV flow rates for both patients, and we can build the parametric diagram of shear-induced platelet activation for both patients, and we can see that absolute critical arteriovenous fistula flow values differ between these patients, and they differ several times. We believe that this developed approach opens the possibility to compare the effectiveness of some biomechanical or biochemical ways of correction the CPACT intensity in the patient-specific arteriovenous fistula. I'd like to thank for Russian Science Foundation and the Kurchatov cluster for their support. This is the authors of this work. Thank you for the attention. I can answer your questions.
Thank you very much, Tatiana, for this interesting presentation. Questions, please. Vitaly.
Well, I can start maybe if
Yes.
Alexey Belyaev, if still here, he is specialist in this question, in this topic.
Actually, this is the answer to our joint question to Belyaev.
Well, Tatiana, okay, thanks, it was nice. Could you please recall us, what is the physiological range for this number of subunits in von Willebrand factor?
Physiological numbers from 20 to 100.
So it changes at such large limits, right?
Yes, yes, it is normal.
And actually, this is spectrum, yes? The distribution.
Yes, it is distribution, yes. And different scientists have different approximations for these distributions, but we use the non-disperse distribution for the von Willebrand factors.
Yes, Tatiana. So certainly I missed something in the explanation of the model, but how do you take in the model into account the number of subunits?
The number of subunits we take.
Maybe you can show the slide.
Yes, yes. I don't share. Yeah. Yes.
No, we don't see your slides now.
Okay. And now?
Not yet, but it is coming. Yeah. Yes. Now it's okay.
The number of subunits is in critical values of cumulative shear stress and shear stress. We take into account only that shear stress which exceeds critical value, and this critical value depends is different for different n.
I see this. The last line is this CSS0 of n, right? Okay.
Yes. And for different n, we have different critical or threshold cumulative shear stress, which can exceed, and when it exceeds it, this von Willebrand factor unfold. And we have the.
That's what I don't understand. Yes, sorry.
We have work where we obtain these dependence. We consider the von Willebrand factor, which can unfold. There are two forces that act on von Willebrand factor. It is the unfolding force and folding force, and we get the equation of unfolding, and there, after the analysis of bifurcation diagrams, we obtain this dependence.
So this function, what is written in your, I don't see the number of the formula 2 or something with the square root.
Formula number 2.
Formula number 2. It is not monotonic, right, as a function of n. Is it right?
Yeah. But if n is more than more 1, it is such.
So it decays as a function of n. First it decays and then it grows, right?
Yes. Okay.
And then I see that Alexei wants to ask a question, but I have one last question. Maybe you can show your slide 13 or 12. 12? 13, both of them. Okay, 13, slide 13. 13.
13.
No, this is which one? Because, yes. For example, yes, so I was just a little bit surprised by this green line that it decreases with the number of subunits. So why, how to explain that? I would expect that if you have more subunits, you would have more activated platelets, but here it is opposite. So can you explain somehow this?
Yes, it is some paradoxical effect, yes, but we think that is connected with the geometry of this arteriovenous fistula, the first arteriovenous fistula. We think that zones for cumulative shear stress is large, for example, for near the walls, but the velocity in these regions is small. That's why such result we see.
Because it's really
the value of cumulative shear stress is big, yes, but the velocity is small. That's why such result.
Well, truly speaking, it's difficult for me to understand like that. Maybe it requires a little bit more investigation. But anyway, thanks. This is interesting. And also, yes. I think Alexei.
Yes, Alexei, please. Yes.
Yes, actually, Vitaly anticipated my first question about this intriguing result with this case you're showing now. But my second question is, what is the actual molecular mechanism that you have on your mind when you link the von Willebrand factor binding to platelets and platelet activation? Is it mechanical stress-induced changes, or is it like chemical signaling somehow?
No, it is mechanical. We use mechanical characteristics that force is acting on von Willebrand. Von Willebrand is unfolding, and more A1 domains become able to connect with GP1B receptors on the platelet surface, and more connections with platelet receptors, more activation we suppose.
Yeah, I see. It's actually quite similar to what we observe in our model, because when platelets bind to von Willebrand factor, they stretch it and they activate the monomers. Now I understand it. Thank you so much.
Yes, thank you.
But as far as I understand, in this model which Tatiana presents, the unfolding is just direct consequence of the shear of the shear rate.
Yes,
That's
we don't use stretching. We don't observe stretching.
Yes, they just directly operate with folding and unfolding of this of the shape of the chain of the molecular chain. That's it.
Yes, yes.
Well, I have maybe one last remark, because the results you show, it looks like they strongly depend on the geometry of the flow.
Yes.
And how these two blood vessels are connected to each other, artery and vein, right? So is it really so sensitive? Because if it is so important, then when they do this operation, it should be very precise at what angle, for example, the artery joins vein. So what do you think? Is this geometry so important, or maybe not so?
Yes, you are sure. It is a big question in the doctors how they can create this fistula. They vary angles and so on. But I'd like to add that there is a very high rate of complications in such fistulas. It is connected not only with thrombus formation, but with hyperplasia, which damage endothelium, and it causes a large thrombus formation. There are a lot of injuries because they need to put needles in these vessels, and it is not so good with arterial fistula. Yes, it is a big problem for doctors. Yes, you're sure.
Yes, okay, thanks. It's nice. It's a nice presentation. It's a nice work. Thank you.
Thank you.
Okay, our session is over.
Well, then I would like to thank all speakers and also our chairman for this very interesting session. And I invite all of you for tomorrow sessions. We have 2 plenary talks and 2 other sessions, so you are very welcome. And I will see you tomorrow. Bye.
Goodbye.
Goodbye.
Goodbye. Thank you so much.